Good evening, everyone. I am Jitendra Bhatia, working with NILAT Chandigarh as a joint director. Today, I am going to present a research paper, Association Rule Mining by Discretization of Agricultural Data using Extended Partitioning Algorithm. It has been written under the able guidance of my supervisor, Professor Anu Gupta of Punjab University, Chandigarh. So, this is the outline of the today's presentation. As an introduction, I would like to brief that mining association rules is a rule-based machine learning technique for discovering interesting relations among variables in large databases. Association rules expresses how items or objects are related to each other and how they tend to group together. Association rules can be classified in various ways based on the type of values handled and level of abstraction involved. Value-based association rules are further classified as Boolean association rules and quantitative association rules. This paper focuses only on value-based quantitative association rules because the agricultural attribute considered for mining the association rules can only include numerical and categorical values, which are the base of mining of quantitative association rules by discretization of data. Various algorithms have been proposed for mining the quantitative association rules. All these algorithms for mining the quantitative association rules are based on a support confidence mechanism. These are five major algorithms to identify frequent item sets for the discovery of association rules. Further, the type of association among the database attributes is depending on the data type of attributes. Database attributes can be classified as quantitative attributes and categorical attributes. Quantitative attributes are numerical and have embedded ordering among values, whereas categorical attributes have unordered restricted possible values. An attribute is called discrete if it has a less than finite number of possible values, while a continuous attribute is considered to have a very large number of possible values. The goal of discretization is to find a set of cut points to partition the range into a small number of intervals that have good class coherence. Many data mining techniques require that the attributes of the data set should not be continuous but should be discrete. If attributes of the data sets are continuous, one has either to opt for a different algorithm or to discover a method to discretize the continuous data attributes before applying the desired algorithm. Discretization of quantitative attributes for mining the quantitative association rules helps to reduce the tally of values. It can be achieved by either using static discretization or using dynamic discretization of quantitative attributes. In the static discretization method, quantitative attributes are discretized before the mining process using concept hierarchies. But in dynamic discretization method, quantitative attributes are discretized into bins during the mining process to fulfill the mining criteria such as maximizing the confidence. Now we will discuss a brief about the limitation of existing techniques to mine the quantitative association rules from large agricultural multidimensional database. During the literature review, it has been observed that both a priori and Princer's search algorithm take too many scans of the database to find the frequent item sets, which reduce the performance of algorithms for mining association rules from large agricultural multidimensional database. Similarly, due to the early pruning of candidates, less representative but important quantitative association rules cannot be discovered by dynamic item set counting method for huge multidimensional data. In the partition algorithm, less representative elements in frequent item sets are being pruned. The procedure to define the support of candidate item sets becomes time consuming. because it needs scanning of full database instead of each partition. FP growth algorithm has also its constraints. For the construction of a main memory-based tree of large multidimensional data, these challenges have motivated to develop a robust method which reduce the computational cost and provide more precise value for mining quantitative multidimensional association rules from huge agricultural multidimensional database. Now we will discuss about agricultural data set. It is a group of related discrete item of data that may be used for various data categories. Considering the agricultural data to mine quantitative association rule to apply right fertilizer on specific crop with objective of high yield, a subset of attributes related to location, size of the farm, crop, fertilizer, and yield data has been identified as an agricultural data set. The extended partition algorithm, which will be referred as EPA, has been developed considering the modifications in principal component of the partition algorithm, which will be referred as PA. In PA, it has been learned from literature that for a large partition size, the number of local frequent item set is similar to the number of frequent item set of the complete database. If the item set are uniformly distributed in all the partitions, then most of the item set derived from different partitions will be common for all partitions. Therefore, the number of frequent item set of the entire database will be limited. The above mentioned state automatically arises when data is incident part of association rule is categorical data and finite in nature. Here, incident part is reflected as a combination of crop and fertilizer, and consequent part is the yield quantity of the crop in quintals per hectare. The data type of Q is numeric. It is continuous data. Hence, the domain size of Q is not finite. This slide shows the comparison between PA and EPA. PA works on principle of partitioning of the incident part P only. Consequent part Q of the association rule has never been considered for creating partition in PA. The EPA has been designed to implement the above mentioned idea by creating the clusters of Q and converting its quantitative data into numerical categorical data using dynamic discretization. This approach aims to reduce the execution time without affecting the mined association rules. In PA, each attribute value pair is represented by an integer, but in EPA, mapping pair of numeric attributes and corresponding categorical values are stored in a hash table. Before the association rules are generated, each number is replaced by its corresponding mapped value stored in the hash table. Initially, when P is categorical data and Q is continuous data, partitioning of Q will create clusters of infinite domain size. Further, conversion of values in each cluster of Q into numerical categorical values will reduce the frequent item sets in Q. Consequently, domain size of each cluster will become finite. Hence, after conversion, it will increase the performance of the system by reducing the computational cost in the implementation of the algorithm due to less number of scans of tables. The EPA is consisting of two phases. Phase 1 sorts all the transactional records under consideration in descending order on the set of attributes P, that is combination of crop and fertilizer, and on attribute Q, that is yield quantity. It creates large partitions with minimum common categorical values of Q with the same value of P. The goal of the second phase is to compute support and confidence for each combination of crop and fertilizer which satisfy the condition of mining yield quantity in numerical categorical form. This is the mathematical representation of the second phase of the algorithm. If computed support and confidence are greater than given support and confidence, then rule will be mined. Here, second step for counting of records which satisfy the condition Q also has a great task to deal. In second step, when database become huge, performance issue will be raised and execution time will be increased. To overcome from this situation, queue has been divided into intervals. Multiple classes or too few classes of quantitative value of queue might not reveal the basic shape of the dataset. Therefore, the number of classes of quantitative value of Q will not affect its efficient mapping into the categorical values of Q. Hence, it is important to decide the number of classes before mapping the quantitative data. The number of classes and class intervals have been calculated using the mapping function and standard deviation. Based on computed class intervals, entire quantitative data of Q can be mapped on logical value of Q. This mapping is stored in hash table. This approach reduces the algorithm execution time and it omits the rules that are not relevant without affecting the main association rules. For implementation and validation of EPA, data has been collected from the State Agriculture Census Department of Punjab. Experimental data of Himmatgarh village of Derabasi Tehsil under Mohali district has been taken. The state government of Punjab has declared 6 crops as major crops, that is paddy, maize, wheat, sugarcane, potato, and cotton. Codes of these crops and applied fertilizer have also been taken as assigned by the Ministry of Agriculture, Government of India. This slide shows the dataset of 72 crop records of Himmatgarh village taken for implementation and validation of the proposed algorithm. These records are stored and sorted on crop code, fertilizer code, and yield quantity in ascending order. The table of this slide shows the number of records for each pair of crop and fertilizer along with corresponding minimum and maximum yield. The calculations performed to determine class differences and class counts have also been shown in this table. Based on the calculation of mapping function, mapping table for conversion of yield quantity from quantitative values to categorical values have been prepared and shown in this table. After mapping of the quantitative values of yield to categorical values, the number of records for mining the association rules have been reduced from 72 records to 21 records. Modified agricultural data set has been shown in this table. The reduction of records also reduced the execution time to be taken by the algorithm for mining the quantitative association rules from the multidimensional database. The crop-wise comparison of the number of mined association rules by EPA and PA has been shown in this slide. It indicates that PA has mined 11 association rules, whereas EPA has mined only 5 identical rules. The remaining 6 rules, having very little support value, are not of much interest. These are highlighted in red color. Each association rule indicated that the expected yield quantity with specified minimum support and confidence when a specific fertilizer is applied on a crop. For example, association rule for weed and ammonium chloride mined from both algorithms indicates that the minimum support of the rule is 30.56%. It also assures with 81.58% confidence that the expected yield quantity of wheat is 42.46 quintals per hectare when ammonium chloride is applied on the wheat crop. The reduced size of an effective dataset indicates that the performance of EPA is better in comparison to the PA for large dataset as support and confidence are being calculated for each unique yield value. Hence, diminished domain size of yield reduce the number of times that algorithm calculates supports and confidence. We can conclude by mentioning that in this chapter, existing algorithm for mining association rules have been discussed and compared. it is found that there is a need to discretize the multidimensional agricultural data for implementation of EPA, which reduce the computational cost and provides effective result for mining quantitative association rules. The idea behind the implementation of EPA is to create group of various attributes. Hence, crop records have been grouped based on the various parameters to create the partitions of antecedent part of the rule. Partitioning of the consequent part has also been done, and its values are converted into intervals to decrease the domain size. Hence, it reduces the computational cost in the implementation of the EPA. These are the papers and literature which we have referred during the work on the paper. Thank you. Finally, questions and suggestions are welcome.